Let's solve this example. The example is that of a sphere rolling down an inclined plane. And no one asked me if there was friction or there was no friction in this problem. And here's the thing. I started the recording. So if there was no friction on the inclined plane, do you think the sphere will actually rotate when it's going down? If there is no friction, there is no reason for my sphere to turn. It will just slide down without rotating. So there must be friction if I actually say it rolls without slipping. So this implies friction. So here I am rephrasing my question. I put a sphere at a point H above my inclined plane. It rolls down without slipping. Question is, what is the final velocity of the center of mass? What is the final angular velocity of rotation? B is find the friction force acting on the sphere during motion. So here comes the important thing. Although there is friction, when I am rolling without slipping, there is no energy loss. Okay. So let me write this. This is an important thing to realize. Although there is friction during rolling without slipping, there is no energy loss. Friction force is static friction. Why is it static friction? Once again, because the atoms on the surface do not see anything going past them. They just see objects coming onto them and leaving. Okay? They may apply a force to them, but they do not. The two surfaces actually do not move with respect to each other. What does that mean in practice? If I have rolling without slipping, energy is conserved. Right? So this is actually quite easy problem to find at least the first part. Can you tell me what is the energy of the initial configuration? Well, there is only potential energy, and I'll be very clever here. I'll choose my reference level to pass through exactly the center of mass at the final configuration. Then what's the height here? H. So what's my initial potential energy? M G H. Good. What's my final energy? Is there any potential energy? No, I choose my reference level to go through the center of mass. How about kinetic energy? How did we write the kinetic energy of an object which is freely moving and rotating? We wrote it in terms of the center of mass motion energy plus rotation around center of mass. So my final energy would be 1/2 m Vf square plus 1/2 I omega square. So these two quantities must be equal to each other. Let me write it. mgh is 1/2 m V final square plus 1/2 I omega final square. But now I have two unknowns, Vf and omega f. But I assumed rolling without slipping. When you're rolling without slipping, these two quantities are not independent. I know that Vf must be R times omega f. And similarly, I was also provided what I was. I was 2/5 mr square. Let me leave it as I for a moment. So here I can write this as mgh is 1/2 m Vf square plus 1/2 I over r square times Vf square. Right, omega f is V over R. So Vf is mgh times 2 divided by m plus I over R square root. Similarly, omega f I can just find dividing this thing by R. Omega f would be square root of 2 mgh m r square plus I. Right? Now, here's a question. And we can probably answer it right away. So I'm drinking a can of soda. If I roll this can of soda off an inclined plane, is it going to go down faster when it's full or when it's empty? Who says full? And how many of you say it's going to go down faster when it's full? Okay. How many of you say the empty can would actually go down faster? Only 2 people. So, well, here's what I have. I have the velocity. So velocity, so this is a can which is empty versus a can which is full. Which one do you think would have more moment of inertia? That's a good question, right?
Is there air friction? Is there air friction?
No, there's no air friction. Do not worry about that.
If they are with the same mass, second one has a bigger amount of mass.
So I am basically I'm not interested in, as you see in my formulas here, I'm not interested in the total mass. I'm more interested in I over R square. Which one is larger? The full one has more I over R square because I actually added more mass to it, right? So here is your assignment. Do the experiment. Okay. So but maybe you should do it before the exam. Okay. That would help you understand. Do the experiment and I'll ask report back next week. So next Tuesday, we're going to investigate that, maybe in a quiz or in some other way. But let me go back. Let's actually, I found the final velocity. Let's find the friction force. So here's my sphere now. It looks like an egg because I drew it, but can you tell me which forces are acting on this object? There are not too many of them. Well, I have mg. I must have the normal force. And I must have the friction force. Which way is friction force acting? This way, down, or up? Well, just, obviously it's going to point up. Why? Because the whole thing is rotating clockwise, right? So that's one way to think about it. That's a friction. Friction. Now, so first let me turn this into a free body diagram. So this is 90 degrees. The angle here is theta. And then I have mg. I have n. So I will actually look at the components of mg. Down the incline, the component is mg sine theta. And perpendicular to the incline, it's mg cosine theta. Can I directly say n is equal to mg cosine theta? Yes, why? Because there is no acceleration perpendicular to the inclined plane. It's not jumping off the plate, right? So that's correct. Good. And I can also say the following. I can say if I find an acceleration a down the incline, m times a is mg sine theta minus F friction, right? That's my second equation. But now I don't know A or I don't know F friction. I need one more equation. And that equation is actually just looking at, staring us in the face. This thing must, if it's going down with A, it must also be rotating, increasing its rotational frequency by some acceleration alpha. Can you tell me what I times alpha is? I times alpha is the torque. Torque with respect to where? With respect to the center of mass. What's the torque with respect to the center of mass? It's going to be R times F friction. Yes?
Why you cannot take those with respect to the platform?
We can do that. But do you remember my, I told you two things for kinetic energy. One formula which was always correct, writing kinetic energy as rotation around center of mass plus velocity of center of mass, kinetic energy of center of mass. Same thing applies here. If you write all your equations in the center of mass frame, you're guaranteed that they're going to be always correct. If you do it with respect to other point, you have to be very careful. Okay? Yes, this is I with respect to center of mass. Okay. If you actually try to, you can, in this problem, that's an aside, you can do it with respect to the contact point because momentarily contact point is motionless. It's like rotating around a pivot, but momentarily. So, long story short, in the exam, when you're solving homework problems, always work in the center of mass frame. Regard all rotations with respect to the center of mass. That's my advice to you. Okay? It may be longer, but it's going to be more straightforward to think about. So here I have two equations and three unknowns, A, alpha, and F friction. But this is rolling without slipping. I know that V is omega times R. If I take one more derivative, A is alpha times R. So here are my three equations which I can solve quite easily. So let me write this as I times, instead of alpha, I'll write A over R is R times F friction, or F friction is I times A over R square, and then plug it back in. M times A is mg sine theta minus I times A over R square, or A m plus I over R square is mg sine theta. A is m divided by capital M plus I over R square times g sine theta. I was asked to find a friction. It's going to be I times m. I'm just going to use this formula here. I times m R square times g sine theta. So for this friction force to act on the system, there must be a static friction coefficient between my sphere and the inclined plane. So I know that this is static friction, and in static friction, the friction force magnitude must be less than mu static times n. So let me write this: I times m divided by I plus m R square g sine theta must be less or equal to mu static times n was mg cosine theta. M's cancelled, g's cancelled. So apparently, for rolling without slipping to happen, mu s must be larger than not only tangent theta, but times this factor of I divided by I over mr square. Okay. Now you can plug in I as 2 over 5th mr square if you want. Please go to your book and read the section about rolling. Okay. I spent 1 hour, maybe a little bit more than 1 hour, but I don't think I actually did enough justice to the topic. Okay. I think it's a good idea for you to go to the book and read that section. In the remaining time, let me review what we learned since the first midterm exam. Now, I'm going to do it in reverse order as always. Okay. So, about rotation, what do you need to remember? You need to remember the definitions of theta, omega, alpha, and then you need to be able to apply dynamical equations where torque is equal to I alpha. You need to remember what torque was, R cross F. You need to remember what I was, integral R squared dm. You need to remember rotational kinetic energy was 1/2 I omega square. In general, K was 1/2 m v center of mass square plus 1/2 I center of mass omega square. And for I, you also need to remember ID square was I center of mass, not square. ID is I center of mass plus m. D square, the parallel axis theorem. And now finally, rolling without slipping. Now, there is not much material. I can write all of this onto a small page, but that doesn't mean anything unless you solve some examples. And I think a good starting point would be the examples that I actually sent to you, the selected problems in your book. Because in high school, you did not learn this rotational motion in detail. Most of you are not practiced in solving problems about rotational motion. Okay? So please solve as many questions as you can. That's the first place where your high school knowledge is not going to save you. Okay? Good. And before that, what did we talk about? We talked about momentum conservation, right? What do we need to remember about momentum conservation? We first need to remember P, momentum, had a very simple definition, just mass times the velocity. It was a vector, but I could actually maybe generalize Newton's second law, saying dP by dt is the force acting on the system. Right? Or I could integrate this to write the change in momentum of any object is equal to F dt, the integral, and that was called the impulse. If I have a closed system, what does a closed system mean? Closed system means the net external force on that system is 0. Then I may have many particles moving in there, colliding with each other. You know, maybe even long-range forces like electrical forces between them. But P total, which is m1v1 plus m2v2 plus all the momenta, is conserved. Why is it conserved? Because of Newton's third law. All forces actually come in equal and opposite pairs, all the internal forces. Good. But we've also wrote that total momentum in another way. We said P is total mass times V center of mass. And how did I define R center of mass? It was all the positions weighted by the mass at that position divided by the total mass. So the center of mass was a very special point. We have already seen how special it is during rotation, right? So for a closed system, V center of mass is constant, which means in many examples, if I have a closed system, the center of mass position does not change. It actually, that observation helped me solve a lot of problems. All right. Specifically, we looked at collisions, in all collision problems, momentum is conserved, but if also energy is conserved, that's called an elastic collision. If objects stick to each other, that's called completely inelastic. And in between, it's just an inelastic collision. Okay, we did not really specify what happens in the middle, but so these two cases you should know well. Let me make a remark here. Not all collision problems have to come with this diagram. Okay, if two objects are attached to each other by a spring, that may act like a collision. Okay, basically any force exchange. If I have a big mass and a small mass interacting gravitationally, so if this mass and the other mass are moving, so that's also a collision. Anytime forces are exchanged between two objects, I can regard that as a collision. And because all such forces obey Newton's third law, total momentum of the system is conserved. So there are different kinds of collision. Good. Before that, we've actually looked at energy conservation. And in energy conservation, what did we say? We say total change in mechanical energy of the system is equal to work done on the system by non-conservative forces. What was the difference between a conservative force and a non-conservative force? You don't remember. But the only thing you should remember at this point is that the only non-conservative force we really think about is friction. Okay, if friction is there, then that's the non-conservative force. All other kinds of forces we've seen somehow are conservative forces. And this, okay, let's look at the right-hand side. What's the work done on a system? It's going to be F dot D only if there is a constant force. More generally, I should write this as F dot dl from the initial point to final point. Okay? And that's going to be final energy minus initial energy. And it can get different forms. First, we had kinetic energy, which is 1/2 mv square. And now that we actually know also rotation, I should maybe add 1/2 I omega square here. And what kinds of potential energy do we know? We know gravitational potential energy, right? Which is mg times h over some reference level. We also know potential energy stored in an elastic sub-object like a spring, which was 1/2 k x square or delta square. Okay, and these two were basically the only kinds of potential energy we know of. Well, except I should come back to the chapter in between them about gravitation. In gravitation, what was Newton's law of gravitation? For any two masses, there was a force which was G m1 m2 over r square attractive force, which can actually be, it's a conservative force, which can be derived, that's only an approximation actually, right? mgh is an approximation to the full formula g m earth m divided by r with a minus sign. So that's gravitational potential. And if I have a attractive force like that, the gravitational attraction force, it actually causes, if I have some planet, I can have stable orbits around these planets. For a circular orbit, what do we know? We know that I can easily find the velocity required to go around this orbit. Why? Because if I'm moving at velocity v, v square r over r times m must be equal to fg, which is going to be g m planet m over r square. In other words, v would be, m's would cancel, 1 power of r would cancel, would be square root of g m planet over r. So the period of the motion would be 2 pi r divided by g m planet over r. So it's going to be 2 pi square root of g m planet r to the 3/2. Or we wrote this in a different way. We said r cube over t square is a constant which only depends on the mass of the planet and Newton's gravitational constant. That was one of Kepler's laws. What were the other two Kepler's laws? The one other was elliptical orbits. We just did this for circular orbits, but in general, orbits are elliptical. And the second one was that when you're closer to the planet, you're closer to the sun, you're actually moving faster. And we're going to investigate that next week. That's just angular momentum conservation. Now, overall, I don't think I've actually missed much here. Although, sorry?
Center of mass.
Well, okay, good. I defined center of mass somewhere around here. Yes. Okay. But you're worried about the technical difficulty of calculating center of mass or moment of inertia for a continuous system. You have to do it by integration, right? And I think it's possible that that may be asked, but we're usually teaching it for preparation for 102, physics 102, where you're going to have to do those integral calculations for a lot of different charge configurations, okay? I think it's a good idea to practice your calculus, but if you already know calculus, I don't think there is no more deeper physics in that, okay? Let me put it like that. Any other questions about the material in the exam? A lot of people ask me if the material from the first exam is included or not. And this thing being physics, it's really very hard to say the material from the first exam is not included. I mean, should we throw out units? Am I going to throw out Newton's second law? Obviously, we would like to test, as professors, the more recent things we have taught you, but that doesn't mean you don't have to remember F equals ma. You obviously have to remember F equals ma. We are building a structure here. You cannot just take the first floor out of a building, okay? So obviously, we would like you to walk on the upper floors, but you still have to pass through the first floor. If there are no more questions, that's all I want to say. I wish all of you good luck in the exam, okay?